we don't need to have a W1, W2 as a function of H1. Right? Now it's come to our mind, then how do we get the independent channels? Right? So here is a special technique known as orthogonal space-time block code, which also provides the channel independency, but at certain cost that we will see here. Yeah. So here you can see a block diagram or a matrix x1, x2, minus x2 and x1 conjugate. This is known as orthogonal space-time block code for a two transmit antenna system. Okay? Fine. So what we are doing here, at the first time instant, we are going to transmit x1 and x2 from these two different antennas. Instead of transmitting the same signal, which we are doing earlier in the beam forming and MRC, here we are going to transmit x1 and x2 in the first frame of time. In the second frame of time, the same signals x1 and x2 are going to be transmitted, but in a modified manner, like minus x2 conjugate from the first antenna and x1 conjugate from the second antenna, right? So it leads to the received signal as R1. You can easily observe here we don't need any weights here to maximize the SNR. So we don't need to have any weights, so we don't need to have any knowledge of the channel coefficients, right? So here R1 and R2 is going to be come in this fashion. Then we will process it, we get the effective channel matrix. This effective channel matrix is going to be orthogonal, and through orthogonality we get the independent channel. If you do the H Hermitian H, you would get the mod of H1 square plus mod of H2 square into identity matrix of 2. Right? Fine? Fine. But then we will process it, we get the effective channel matrix. This effective channel matrix is going to be orthogonal, and through orthogonality we get the independent channel. 2 time frame. So we need extra power, right? The power is going to be divided. The total power is going to be divided. Right. So before showing the comparison between the different techniques which we have just go through, MRC, beam forming and OSTBC, I'm going to just give you the basic introduction of this bit error rate versus SNR graph, this waterfalling graph, and what does this gap and slope represent. Okay. So the gap is represent the coding gain. This coding gain represents the how much SNR we would require to achieve the same bit error rate, right? If I say as an example 10 raised to the power minus 4, this is our bit error rate. So you can see to achieve the same bit error rate, we required lesser SNR for the curve shown beneath, right? At the other side, this blue line shows the different slope. This blue curve shows the different slope, right? And this slope represents the diversity gain, right? These two curves having the same diversity order, we can say, let's say 2, so follows the same slope. However, this having a different slope, which is a greater slope, so this may have a diversity order 4, right? So here you can easily see the comparison between the different configurations using different signal processing techniques, like this dash line where we consider only one transmitter and one receiver, right? Slope would be 1, only one channel, diversity gain would be 1, right? Then we have a Alamoti 2x1 system where we don't need any channel state information, right? So it provides the diversity order 2, similar to the MRC and 1x4 system having the slope of 4. So this graph reflects the different diversity orders and the coding gain. If you can compare the coding gain between the Alamoti 2x1 represented with this dark line with asterisk and MRC 1x2, you can easily see the difference. You can easily see the difference of the coding gain between these two lines, isn't it? Gap. Why we are facing this gap? because of the in LMOT we are going to transmit signals in a 2 time frames, which needs more power, which needs more power. To achieve the same bit error rate, we need to transmit more power in LMOT case. That's why we are having a gap here. Whereas in MRC, where we have a channel state information available, so we are getting lower power to achieve the same bit error rate. Fine. So what would be the solution between these two things? Here, in one technique, we need full channel state information. In one another, we don't need any channel state information. It's like an example. Whenever you are looking to go somewhere, you set a destination on the Google map, you get a different path to achieve, to get through, right? So on the basis of the time, sometimes distance, you shortlist your path, right? So before starting your journey, you have the knowledge of your path, isn't it? Accordingly, you choose the best one, best suitable to you, right? So in this scenario as well, what I am saying, before transmitting your signal, you need to know the knowledge of the channel, which channel is the best, so that we can put more power to that channel, right? So this is the situation. But if we don't have a Google map, तब आप क्या करें? Then what you will do? If you don't have any kind of technology in your hand to choose the best route, what you will do? Experience, you need to do lots of effort to reach there, right? Right? Accordingly, petrol would cost, time would cost, right? So in a similar manner, what I am saying here, we lost a coding game here. This gap, right? It reflects how much power we lost. We don't have the channel state information. However, we get the diversity order same, right? Signal is transmitting through the both the channels, right? Fine, but with a more power. Fine. So the solution lies in a channel state information acquisition, right? You say it seems like if we have the option of full channel state information acquisition, why don't we choose the simple beamforming and MRC technique here? But what about when we have a large number of antennas, like 100 and 1000 number of antennas? It would not be possible for us to estimate the full channel state information for all the antennas, right? Latency would be high, bandwidth feedback overheads would be high, right? So what we propose here, partial channel state information, right? Partial channel state information means we would acquire the channel state information but partially, right? So this is what we propose, the feedback part, right? The first part is quite well-known technique how to acquire the channel state information at the transmitter, but it requires lots of calibration, and this calibration for the massive number of antennas is not always possible, right? So through this feedback, what we do, we estimate the channel information at the receiver side. If I am assuming here B is the receiver, right? Then this receiver side feedback that information to the transmitter, right? In what manner? In what form? That is the whole catch here, right? So through the quantized manner, whatever we are going to achieve, we quantize it in the form of bits, like 0, 1 if we have a 2 channels, right? If we have a 4 channel, then it would require how many bits? 2 bits, right? 0, 0, 0, 1, 1, 0, 1, 1, right? So through this, the advantage is like we don't need to overhead, increase the feedback overhead to provide the full channel state information. See, channel state information means values of the channel coefficient. Okay. Values of the channel coefficients is a complex number x plus iota y that I am going to display through the MATLAB code to make you understand. Okay. So what would be the challenges in this feedback thing? It might be possible whatever we are quantized, it get corrupted while transmitting through the feedback channel, because that feedback channel also a wireless channel, right? So it might be possible it also faces a fading and it may get corrupted, right? The second is the rate of the feedback. There would be a delay in the feedback, and that delay is quite significant. In the meanwhile, we have forward channel का जो information है that got changed. Meanwhile, we have a feedback, right? That I am going to show here. See, okay. So I'm going to start with this the simplified technique where we combined OSTBC with this feedback technique. Okay. OSTBC, orthogonal spacetime block code, is used to make the channel independent, right? And while transmitting, it requires more power, which leads to coding and loss. Okay. So instead of that, we put a precoder. Okay. This precoder would allocate the power to the antenna associated with higher channel gain. Okay. As I have told you, at the receiver side, it estimates the channel information, right? Then quantize it in the form of bits fed back at the transmitter, where we choose the precoder accordingly. For example, if the feedback bit is 1, it means we need to choose W1. Means H1 is having the higher gain instead of H2. So here is a precoder structure. A square 1 minus square, it's a diagonal precoder structure, and as I've explained you, if the gain of channel 1 is greater than channel 2, we would choose W1, otherwise W2. Okay, fine, we choose W1. Then what next? What would be the values of the A square? How do we choose that? If I choose A square as 1, it means I'm going to allocate whole power to the single antenna, isn't it? This W1 would become 1, 0, 0, 0 if we choose A square as 1, right? So it means whole power is going to allocate to the H1, right? What do you think? It's the best thing or not? If we choose A square 1, once we have a feedback information through which we select W1, then can we always select A square equals to 1? Can we always select A square equals to 1 or not? If we choose A square equals to 1, then it means we are allocating whole power to the single antenna, single channel. So what do you think? Is it the best thing? We all need a multitask, a multi-purpose thing, isn't it? Like you are already doing here, multitasking, isn't it? So we need to distribute our power so that everything is going to be conducted in a smooth manner. Right? So let's say our feedback bit get corrupted, and through which we selected W1. If we provide whole power to the single antenna, and that single antenna is in the deep fade situation. Deep fade situation means in a very bad condition. Channel gain is very bad. But due to the feedback which may get corrupted, we choose a wrong antenna and provide all the power to that. Right? All of you aware about maxima or minima, right? Right. Okay. So what I am doing here, just selecting the maximum channel gain, max of H1 and H2, right? Right. So if my feedback information is correct, then it would be fine to choose the max one and provide whole the power to that. But if my feedback information is incorrect somehow due to the wireless fading of the feedback, so it means I am choosing a minimum one, which would not provide the sufficient communication, right? Okay. Again, if we choose a square equals to 0.5, then what does it mean? We are giving equal power to both the antennas, 1 by 2 and 1 by 2. Both the antennas would get equal power, right? So what do you think? Then what we are doing with the feedback? If we have to give equal power to both the antennas, then what is the purpose of doing the precoding? There is no such purpose, right? We don't need to estimate the channel. Na? If we are giving equal power to both the antennas, then we don't require any information of the channel, right? Right? Like in a stock market, if you have a portfolio, right? X1, X2, X3, if you have a 3 shares, right? And if you have a 120 rupees with you. So what you 40 rupees you would invest like this. So it would make a uniform power allocation, isn't it? So what do you think? You go through the data, Hana, which one would be the lower risk, stable, and accordingly you would invest, right? It might be a 60, 40, 20, right? So you need to have an optimum value. You need to have an optimum value of your investment. Similarly, we are looking to have the optimum value of this A square, right? So that in case of incorrect feedback as well, we having a selection of the channel with maximum channel gain. If we completely shut down one channel and giving whole power to the single channel, and that channel in the deep fade, so it would not provide the desired communication performance, right? So the whole purpose is here to find out the optimum value of A square, right? So how do we find the optimum value of A square? As I've given you the example of the stock portfolio, right? So how would you find, if you put the weights on your portfolios like W1, X1 plus W2, X2 plus W3, X3, you need to have the value, optimum value of these weights, right? How would you find? In a stock market, we have a volatile response, right? So it means variance. So you would find a variance. You need to find the variance point where it get minimized, and that would be your optimum value, right? Similarly, in a communication, we have a bit error rate, symbol error rate, outage probability. These are the performance metrics we have, right? So we need to minimize all these parameters, right? Right. So first, we need to find out the instantaneous SNR before analyze the bit error rate, right? So this would be the instantaneous SNR. The first expression represents for correct feedback. When we have a correctly decoded our feedback information at the transmitter, right? Second one is the reverse. Yes, you can see here. A square, 1 minus A square, and second we have a reverse thing. Reverse means we selected a wrong recorder due to the corrupted feedback. Right? This T and U is just, I have explained you, max and minimum. Okay. To compress this expression, we use this kind of variables. So here is an example to elaborate it. We have a 2 channel gains. One is 5.2, another is 2.8. So we would choose W1, right, to allocate the power to the H1. So if we choose A square as 1, so our W1 would be 1000, and 100% of the transmit power is going to allocate to the antenna 1, right? Right. And in another case, when we have a mod of H2 square greater than mod of H1 square, we choose W2, right? But this is not the good option always, because it's due to the wireless phenomena, we may have get corrupted quantized feedback rate. So instead of that, what we do, we're looking to find out the optimum value of a square. For example, for a square 0.6, it means 60% of the power is going to be antenna 1 and 40% to the antenna 2, right? So how do we find out what would be the optimum value, 0.6, 0.7, 0.8 or 0.9, right? So on the basis of this bit error rate, we minimize this bit error rate and find out the optimum value of a square for different values of PC. This PC represents the probability of correct detection of feedback, right? That feedback link, what would be the probability that we would get the corrected feedback, quantized bit feedback at the transmitter through the receiver. If we have a 80% probability we decoded correctly, so we get a square as 0.7. It means 70% is power is going to allocate to one antenna and 30% to another, right? So according to the probability of correct detection at the transmitter, we choose the optimum value.
If we do the
Right.
H Hermitian
So it's
H,
a
we would get the
convex
mod of H1
curve,
square plus
see,
mod of H2
as
square
we
into
increase
identity
the
matrix
value of PC, it
right? Fine.
we get the
Fine.
leads to the
But then
what
we will
are
process
the
it, we get the
cons of
effective
this.
channel matrix.
If
This
we
effective channel
are
matrix
quite
is going
sure
to be
we need
orthogonal,
we
and
receive
through
or
orthogonality we
the
get the
feedback
independent
correctly at the transmitter,
times,
right? Then
so we
can
need
easily choose the
extra power,
best antenna and
right?
allocate
The power is
whole
going
power
to be
right?
divide. The total power is going to
So
be
on the
divided.
basis of this,
Right.
On the basis
Right.
of this,
So
here,
before showing the
this figure
comparison between
represents
the different techniques which
the
we have
equal
just
power
go
allocation
through,
and the
MRC,
optimum
beamforming
power
and
allocation
OSTVC,
graph,
I'm going to
right,
just give you the
where
basic introduction.
we have M represents the fading scenarios, right? Larger the value of M, lower the fading scenario we have. That is with the help of the Nakagami M distribution, right? So here you can observe we have a specifically three patterns of curve. The first dash dash curve represents the equal power allocation, right? As I have told you, A square equals to 0.5. So equal power is going to be allocated to all the transmit antennas. Right? In between, we have this asterisk curve, which represents when we get the corrupted feedback, and we give all the power to the single transmit antenna. So it loses the diversity order, right? Because it chooses the wrong antenna, right? Instead of that, if we use the optimum power allocation using these values, we would get the higher diversity order and more coding in comparison to the equal power allocation, right? This phenomena of feedback is quite useful in the financial signal processing as well, financial signal processing, right? Through which we can optimize our thing as per our performance metric. Okay. So we extend this work for n number of transmit antennas or MIMO systems with quantized feedback bits. Right. Right. Okay. So for n number of precoder, how many bits we would require? As I've given you example of two transmit antennas, we need two feedback bits, 0 and 1, right? If we have a 4 precoders, we need 2 bits to select the precoder 0, 0, 0, 1, 1, 0 and 1, 1. Then for n number of precoders, how many number of bits we would require? Log base to n, right? Round up of log base to n, right? If we have n equals to 4, so it means we need 2 bits, right? If we have n equals to 8, we need 3 bits, right? So for n transmit antennas, we have designed a precoder structure, a generalized precoder structure for n number of transmit antennas. A1 minus A square, this n minus 1. If you select n as 2, so it leads to A square 1 minus A square, right? So here we have an instantaneous SNR expression. It's a quite important expression, not easy to express this while we were working on this. The first SNR expression is for correctly decoded feedback bit, right? This x1 represents the first channel gain, which would be a higher than the other one. Again, we find out the optimum values, and with the help of this, we get the second figure with BTAS, best transmit antenna selection with no feedback error. It means we get the perfect feedback at the transmitter and allocate whole power to the single antenna, right? This magenta one represent that one. UPA, uniform power allocation, you can easily see the difference between these two, the coding and difference between these two. Then we have a fixed SNR ETW. It means ETW means optimum power allocation, error tolerant weighing, right? If we have a 5% feedback error, 5% feedback error means PC is your 0.95. 95% probability you get the feedback decoded correctly and 5% errorness, right? Right. So since we use the optimum power allocation for 5%, means we choose the optimum value as 0.86. So we don't lose any diversity order. However, where we choose to select a single best antenna in the case of feedback error, right, we lose the diversity order. Then the most interesting part of this work is SATW, SNR adaptive error tolerant weighing. What does it mean? I'm not going to manually set the value of A square. It's quite a tedious process for me to always find out the value of this A square because I don't know what would be the value of PC, right? I don't know what would be the probability that we would get the corrected feedback or incorrect feedback. So what we have done here, we make it adaptive. We find out the bit error rate of the feedback, okay, as a function of PC and A square. So it automatically adapts accordingly as per your SNR value. Fine. Then we led to MIMO for this particular thing, including generalized OSTBC encoder. GOSTBC represents generalized OSTBC encoder. Fine. So we have formulated this recorder structure in a very compact manner where this I represents the number of receiver antennas and J represents the number of transmit antennas, right? So how do we choose here which one is the best transmitter? If I am saying we have an NT number of transmit antennas, then how do we choose which one would be the best? We would sum all these channel gains which is going to attach with all the receiver, from the single transmitter to all the receiver. We add up all these channel gains and find out which one would be the maximum. This norm square is the addition of the mod square in terms of vectors, right? So if you consider it as a matrix NR cross NT, right? So it's a sum of your first column, sum of your second column, right? Sum of your first column represents all the channels associated with your first transmit antennas. Fine. So here you can see we get a similar kind of trend for 8 cross 4 MIMO systems, right? For different values of M. As I have already explained, M represents the fading severity. Larger the value of M, lower the fading we have. ठीक? So you just need to focus on these red dash and this magenta one and green. These three are the prominent one. You can easily observe here. We giving whole power to the single antenna. In case of erroneous feedback, we lose the diversity order as well as coding gain for whatever the value of M. However, if we use the optimum power allocation, ETW, error tolerant weighing, we won't lose the diversity order, and this graph lies between the uniform power allocation and the best transmitter selection in case of corrected feedback. Right? Then we compare the coding gain between this BTS, best transmitter selection for perfect feedback, and equal power allocation, uniform power allocation UPA, with respect to NR and NT. As we increase the value of NT, we can observe here we achieve the higher relative coding gain. However, as we increase the NR, it relatively decreases. Why? While increasing NR, we are not getting the desired output as a relative coding gain. Why? Because it leads more signal processing, right? So it becomes a trade-off. It becomes a trade-off while increasing the NR value. Fine. Then we apply this phenomena for the cooperative communication, having the source with a single antenna, two relays, and a single antenna based destination. So again, we use the same phenomena of feedback from the destination to relay to choose the best relay antenna, right? Here we use the decode and forward protocol, which means first these relays would decode whatever it achieves, then again encode it and retransmit to the destination. We have two kinds of decode and forward phenomena. One is selective relaying and another is fixed relaying. In selective relaying, it is going to transmit the signal when it having the SNR value larger than some threshold value, right? So here we use the same phenomena, find out the optimum value accordingly, and pattern would be the same. For large value of PC, we have a higher value of A. So here instead of BTAS, we abbreviated it as BRS, which represent best relay selection, right? So again, in case of erroneous feedback, if we give all the power to the single relay, this going to be deteriorate our performance, right? Okay. Now we have a dual hop, dual feedback MIMO system, right? We fed back uh, information from the R to S relay to source and then destination to relay to select the best antennas at every hop, right? It's quite interesting one. So here we have a precoder design for first hop from R to S and same precoder design with different weights for D to R. So precoder structure is quite same which we have used for the MIMO system earlier. Okay. So here is an example for that MIMO system. this capital uppercase H represents your channel matrix. Its dimension would be NR cross NT. NR represents the number of receiver antennas and NT represents the number of transmit antennas. Where for 2 cross 2 system, NR equals to 2 and then NT equals to 2. If we have this kind of situation where H is 1.8, 1.2, 1.4 and 0.8. So norm of H1 square is the sum of first column, as I've told you. Sum of first column, square of sum of first column, 1.8 square plus 1.4 square, 5.2. And sum of second column is 2.08. It is quite clear that channel 1 is having a higher channel gain. So we choose the first antenna, and accordingly precoder would be W1. We give all the power to that first antenna. So it means 1000, right? So what we have additionally done here, we looking to find out the optimum value of the weights for first hop and second hop simultaneously, right? Because our outage expression for whole this end-to-end connection would be the in terms of weights of first precoder and weights of second precoder. So we can easily find out the optimum value jointly, right? So we have a this 3D graph which represents the optimum value 0.75 and 0.75 for the first hop and second hop for the given conditions, like PC1 for the first hop and PC2 for the second hop, that is 0.95. This 0.95 represents the 5% of probability of error in the feedback, right? So we achieve this graph with that help of the optimum values, including the asymptotic uh, curves. So the very first situation where we don't have an error at the first hop and second hop, no error in the first while we are selecting the best antenna at the source side and best antenna at the relay side. EPA equal power allocation for the both the hopes. We are providing equal power to the source and relay. Then the worst case scenario where we have an error in the first hop and error in the second hop, and we use the optimum power from this graph. For 5% error, we have a 0.75 and 0.75. So you can see here when we don't have any error, still we are using the optimum value. And here we have an error, we are using the optimum value. So observe on this red diamond and green one. They are quite coincide with each other due to the optimum values. So optimum values are dominating here instead of error. Fine. Okay. So this is a comparison of asymptotic outage probability for SNR adaptive error tolerant wing, which I have already explained you. SNR adaptive means our feedback probability of error of the feedback link is going to be adaptive according to the SNR. Okay. So automatically it sets the value of PC, it chooses the optimum value of A square and adapt accordingly. So whatever the value of M1 and M2, here we also included one term M1F, which means the fading in the feedback, right? M1F represents the fading in the feedback of the first hop and M2F represents the fading in the second hop. So instead of having any value of MF and the forward M1 and M2, we have getting the similar performance that magenta dot and the purple line are coincide each other beautifully, right? Which shows that this SNR adaptive error tolerant wing scheme is quite robust to every scenario. So we have a different performance metric here instead of outage probability we have a symbol error rate here. So similar to the outage probability, we can see the same trend in this graph as well. Now, okay, so we applied this in a eavesdropping thing, physical layer security, where we have a eave between the transmitter and receiver. So in a physical layer scenario, we called it as a Alice and a Bob. Alice is a transmitter and Bob is a legitimate receiver. So in between we have a eave. Okay, fine, fine. So what we have learned so far, try to uh, compile all such things before understand this one. What we are doing, we are providing the feedback information to the transmitter. Accordingly, choose the precoder, right? Choose the precoder. Whatever precoder have been selected at the transmitter side, right? The same precoder will work for the eavesdropper as well, right? Fine. But it doesn't mean that the same precoder will be the best one for the eve channel, isn't it? Because the recorder which we have selected is based upon the legitimate channel from the Alice to Bob, right? It might be possible that the same precoder would be the best for the eve at that instant, isn't it? Uska bhi channel gain is going to be high at the same time. For example, if you are choosing the first antenna according to the H1, it might be possible that at the same time G1 would be the high. So all the information would get leaked to the eavesdropper as well, isn't it? But it is not going to be happen always. So we average it as a secrecy outage probability, right? Based upon the iterations, right? We are going to average it, and while averaging it, we can observe that we are getting the this kind of trend which we have achieved for the simple outage probability without eve. Fine. See. So why we are achieving the same trend in the presence of the eve here? This is the question. Why it is not affecting our optimum value? Why it is not affecting the performance gain? Because whatever we are choosing is based upon the H1 and H2 legitimate channels, not based upon the G1 and G2. Fine. So it's quite useful observation that we can use the same feedback signal processing here in case of eavesdropper. Okay, fine, fine. So what we have here, we need to have log base to n number of feedback bits to provide the channel state information from the receiver to the transmitter for n number of transmit antennas, which is quite high. For example, if we have 256 antennas, it means we would require how many bits? 8 bits, right? So accordingly, if the antennas count increases, feedback bits count also increases, right? So to reduce the feedback overhead, what we choose, we make a cluster of antennas. We divide the whole transmit antennas into two clusters. It's a very first and what should I say, suboptimal scheme. Yeah. So from these two clusters, we are going to select only one cluster. Out of these two clusters, we are going to select one best cluster. So how many bits would we require? Out of these two clusters, cluster means to divide the whole number of transmit antennas into two groups. To select the one group, how many bits we would require? 1. Only a 1 bit. For bit 0, we would select cluster 1. For bit 1, we would select cluster 2. So only 1 bit would be required. However, we have how many antennas? NT. So we reduce the required number of feedback bits from log base to n to 1. Fine. But the performance is not going to be comparable. Why? Because this is a suboptimal scheme. It might be possible that the best antenna with the higher channel gain is in another cluster which we haven't choose, right? For example, if we have a 4 antennas and 2 antennas in a cluster, right, and the channel gain distribution is like 2, 3, right? It means total would be 5, right? And another one is 1 and 4 equal हो गया, right? And if we choose a cluster 1, 2 and 3, so we neglected the antenna having the highest channel gain 4, right? So it's a suboptimal scheme, right? We reduce the feedback bits, but as well as channel gain, right? So here's a precoder structure. A1 and A2 have been formulated as 2a square by nt. If for nt equals to 2, you lead to the 2 cross 1 system again, right? If we have nt equals to 4, so it means a square by 2. Matlab 2 antennas would get a square by 2, a square by 2, right? So how do we select the best cluster precoder, W1 and W2? And this is the performance. As I've told you, I think I have not included the comparison between that two in this. Later on, I can show you. Right. Fine. So, in a cooperative manner, we first hop we have applied satellite communication here, and in the second hop we have a terrestrial communication in the presence of Eve. Right. First scheme, log base to n number of feedback bits, select the best antenna, allocate the power optimally. Okay. Second, selecting the best cluster to reduce the number of feedback bits, right? Required only 1 bit. Okay. Now, in another scenario, here we have to select best two antennas. To select best two antennas, right? And in another one, this one, we again divide the whole antennas at the relay in the two cluster and select best antenna from that cluster. Single best antenna from the one cluster and another single best in the second cluster, right? Fine. So we have formulated all these schemes by ourselves and then compare it. Okay. So there are two things need to be compared. One is how many number of feedback bits we would require, and second is coding gain performance. Fine. So here we have summarized all the things. We applied eavesdropping here. We applied the best two antenna selection and the cluster scheme as well. Okay. So here we have a precoder structure for this selecting the best two antennas. This kind of precoder structure have not been exist in any kind of research, right? So instead of log base 2n, now we need only log base 2 n minus 1 by 2 number of bits. Okay. So as compared to the number of feedback bits, we able to reduce it, but not that much, but still comparable. So to understand that precoder structure, it is quite easy to understand with the help of the bit mapping. Okay, fine. Fine. So for n equals to 4, here log base to n minus 1 by 2, for n equals to 4, what would be the value? Log base to n minus 1 divided by 2. For n equals to 4, what would be the value? 4 into 3 divided by 12, 12 divided by 2, log 2, 6. Log 2, 6, how much it is? Approximately log base to 6. Yes, log base to 6. All of you have a calculator in your mobile. Two point 585, मतलब 2.6, right? Fine. So we don't have a capability to choose 2.6 bits, right? And I have put a ceiling function here, need to do a round up. So it means we need 3 bits for n equals to 4, right? Fine? Fine. So for n equals to 4, we have 3 bits. So here you can see 0, 0, 0, 0, 1, 0. These are the patterns of feedback bits we have, and accordingly we can choose our precoder. Accordingly we can choose our precoder. So we choose precoder W12. What does this W12 means? First antenna and the second antenna are the best two antennas, and we allocate A1 power to these two antennas. Okay? So in case of negligible fading in the feedback condition, and we are assuming that whatever we are achieved through the feedback, it is quite accurate. So we allocate power accordingly. All the other cases are erroneous cases, but based upon the fading condition, we have a weak fading, moderate fading, and severe fading. So if you see the strong fading last condition, it's a quite reversible of the first condition, right? This U1, U2, U3, and U4 represents the channel gain of first antenna, second, and third and fourth, right? Right. Fine. In a second scenario where we divided the total number of antennas at the relay into the two clusters and selecting the best antenna from the east cluster. Selecting best antenna from the east cluster. So we need an additional bit here, isn't it? To select the best antenna from the every cluster, we need an additional bit. Okay. Fine. So again here for 4 number of for 4 number of antennas at the relay, we need 4 bits, 2 bits, sorry, 2 bits only. So this is the pattern we would have 0, 0. Are you able to understand this? C1 is your cluster 1, X1 and X2 are the channel gains of the antennas in the cluster 1, and X2 and X3 and X4 represent the channel gain in the cluster 2. Fine. So 0, 0 means negligible fading in the feedback scenario. So we choose the best antenna from the first cluster, that would be X1, and allocate power A1 to that. And best antenna from the cluster 2, that is X3, and allocate A1 power to that. Right? So accordingly, we have a combinations here. In case of erroneous, we have a 0 and 1, moderate fading. 0 again for cluster 1, feedback bit 0, we choose the X1 from the cluster 1. Whereas for erroneous case in cluster 2, we allocate power A1 to X4, which is in the deep fade. So here is a feedback bit, required feedback bit comparison between these two schemes, including SRAS. This SRAS represents the single antenna selection, single relay antenna selection. जो हम बात कर रहे थे log 2n की, राइट? I am talking about the this negligible fading of the feedback channel. Feedback channel. Yeah. So for n equals to 3, the first scheme B2RS, the log 2 and n minus 1 divided by 2, we would get a 1.585 ceiling function with 2 bits. Similarly, for CRS, where we divide into the cluster, we need only 1 bit. SRS represents selecting the best antenna out of 3. We require 2 bits, right? So we have a comparison here. You can compare for n equals to 8, which provides you the difference between these 3 schemes, right? Fine. To select the best antenna, it requires the lowest feedback bits, right? Selecting best 2 antennas requires the highest number of feedback bits, right? So what do you think? Selecting best 2 antenna would work better than the selecting best single antenna or not? Which one would be the beneficial for us? Selecting best 2 antennas or selecting a single best? See, both of them provide the same diversity order in case of correct feedback. In case of correct feedback, both of them provide the similar diversity gain. Selecting best, see, there is a trade-off. Selecting best 2 transmit antennas require higher number of feedback bits. However, in case of error, how many number of antennas actually working? 2, right? Whereas in case of single antenna selection, in case of error, only one antenna works, right? And that is illustrated here. You can see the comparison between these 3 schemes: B2RS, CRS, and SRS. Fine. See where we have considered eavesdropping here, right? Whenever we have a eavesdropper, we called it as a secrecy outage probability. Instead of simple outage probability, we called it as secrecy outage probability. That's why you can observe at the y-axis we mentioned that SOP. Okay, that represents the secrecy outage probability. How much information have been leaked towards the eavesdropper? Yeah. So at the starting where we have a lower SNR values, single relay antenna selection SRS works best, right? Right? As the SNR increases, we have a cross point and it B2RS outperforms SRS, right? As we increase the SNR, the more information is intended to leak towards eavesdropper. And if we select only single antenna, right, so it leaks more information to the eavesdropper instead of selecting 2 antennas. It's let me explain it one more time. Selecting best 2 antennas and selecting single best antennas. We are looking to compare these 2 things, right? How in a cluster relay antenna selection CRS scheme, we are selecting best antenna from each cluster. So in a way, we are activating 2 antennas, right? Right. So activating 2 antennas and activating a single antenna. We are comparing the comparison of these 2 things in the presence of the eavesdropper. Right. What do you think? What would be, which one have a higher probability? That single antenna would be the best one for the eve at the same time, or having 2 antennas best for the eve at the same time? Which one having the higher probability? You are looking at as a, we are selecting two antennas and you are saying the probability of selecting two antennas and it would be the best for the eavesdropper at the same time is higher. No, it's more confusing for the eavesdropper because I'm talking about the at the same instant of time. At the same instant of time. Let's say if you have to pick a pen out of two, right? You pick a one pen, so probability would be 1 by 2, 1 by 2. And if you need to pick one pen out of four or two pen out of four, right? Are you getting this? So it would be a more confusing. If I name it as A, B, C, D, four pens, and you need to select two pens, that would be the correct one which I have mentioned. Selecting a two is more difficult. It's more confusing. So it's a more confusing for the eavesdropper to having the that same two antennas which are best for the bob and same for the eve. At the same time, it is quite difficult for the scenario, right? So that's why you observe the cross point here. That SRS performance deteriorates as the SNR increases. Okay? Because it leaks more power towards the eavesdropper. The confusion is lower for the eavesdropper to having the single best antenna, right? So the first one is for all these things for the correct feedback. Okay? And the second graph represents for the erroneous case. B2RS for erroneous, C2RS for erroneous, right? And I think I missed a SRS. SRS erroneous is not considered here. Okay. Okay. So SOP versus PE. As I've told you, PC represents the probability of correct detection of the feedback bit at the transmitter, and PE represents the probability of feedback error, right? So as the probability of feedback error increases, outage probability also increases, right? Now, the second phenomena, as I've told you, in a feedback technique, we have two challenges. One is imperfect feedback, error in the feedback, and second is delay in the feedback, right? So now we are looking to combat the second challenge where we have a delay in the feedback. What do you mean by delay in the feedback? We estimated a channel at the receiver, then looking to pass this information to the transmitter through the feedback link, which would be a wireless link. And due to the delay spread in the feedback, our information get outdated, right? Our forward channel values get changed while we receive the feedback, right? That's known as delay. So we try to make our system delay tolerant as well instead of only a imperfect. Okay. So now it represents with this hj hat equals to rho hj under root 1 minus rho square w, where hj and hj hat, see, hj is your accurate channel information and hj hat represents the outdated one. Okay. It depends upon the correlation coefficient of both of them represented by rho. If this value of rho is 1, it means h hat equals to h. There is no such delay. And if there is rho is equals to 0, it means h hat is equals to w. It means totally outdated. Okay? Totally uncorrelated. In a wireless channel phenomena, we have a certain time limit after which the channel gets changed, right? It's a dynamic time varying channel, right? So after a certain milliseconds, it gets updated or changed. If you observe it with the help of the convolution, right, or a circular convolution matrix where you have a rotated values, right? So here you can also have a rotated values in a first frame of time. If you have a h1, h2, h3 and h4, in a second time you have a updated values. Not all the values may get updated. You may have updated of last 4 values or the first 2 values. So there is a correlation between the previous vector and the updated vector, and that correlation is represented by this rho. It might be possible that delay is quite significant, that is this rho is equals to 0. All the values of that channel vector get changed while we receive the feedback. Okay, fine. So what we need to do here, we need to find out the distribution of this h hat to proceed. Okay. So again, what we do, we allocate the power according to the delay. Fine. As we are giving this power according to the optimum value related to PC, probability of correct feedback, where we consider the imperfect feedback. So here we would see the delay in the feedback, probability of delay in the feedback. Instead of PC, now we have a PD, right? And we called it as best antenna full power allocation with the delay and without delay. If we have rho equals to 1, as I have told you, as you can see here, if rho is 1, it means h hat is equals to h, there is no delay, right? So no delay, it means probability of delay is 0, PD is 0. And second case represents with delay, where we have a rho is between 0 and 1 and PD can't be equals to 0, right? So we use a simple trick here to make it a delay tolerant as well, right? You can yourself extend this work for different distributions. We have done, I think we have done it for Raishian fading. You can done it for Nakagami fading, but for that you need to do a moment matching here to find out the PDF of h hat. That have been explained in this conference paper, how to find out the moment matching and how to find out the PDF of hj hat. Again, we use the optimum value according to the value of the PD, probability of delay in the feedback, right? And we achieve the same pattern as we have achieved for the imperfect feedback, and it shows we able to achieve the delay tolerant feedback. Okay. Now, whatever we have discussed so far, it is for RF communication. We can use this feedback scenario for FSO communication as well, free space optical communication. It's quite trending and emerging technologies. It have been used in the underwater optical communication as well. So it has certain advantages and disadvantages as well, right? It having a advantages of speed and flexibility. Instead of using a fiber, we can use the laser here, and the speed is quite significant, right? It works upon the line of sight. You can call it as a more secure, and trade-off is it's a quite directional. We can't do a multi-directional thing with the help of this laser, means broadcasting can't be done, right? And since it works up with the help of the laser light communication, it having a severe uh, fading conditions like atmospheric turbulence, right? Eddies, that is the main word here. How eddies means the combination of hot air and the cold air. All of you have observed the tandoor, right? All of you have seen the tandoor, है ना? We have a tandoori naan, right? Jatin, most of have it, है ना? हाँ, ठीक है. So we have a tandoor, right? And hot air coming out of it mixed with the cold air, right? And we clearly see a wavy picture, right? Through that through that flame, we can easily see the wavy picture. If you pass a laser light from that flame, na, it also get deviated. That is known as turbulence, right? That is known as turbulence due to the atmospheric condition. When the hot air mixes with the cold air, it leads to eddies in the atmosphere, which leads to the atmospheric turbulence. It is one of the scenarios, right? We used to have a turbulence in the airplane. You know? We use this word for the airplane, right? Turbulence, right? It means wavy. Right? So we have a higher data rate as advantages, including easy to deploy, right? And we have so many applications. Likewise, now we have a Li-Fi, VLC, all such things. And limitations, as I've explained you, it needs a line of sight, and atmospheric turbulence deteriorates its performance. And we have a pointing error as well. See here, we have a laser here, and my hand is not able to so stable. We can easily see a deviation, right? So we have a, for example, we have a aperture here. Aperture here means we have a receiver diode, right? Photodiode. We put a light on it, right? It provides the information. So my hand is not that much stable. We always have a wavy thing here, right? Fine, right? If I put or deploy it on the stable platform, it remains stable, right? If we mount it on the building, right? But due to the thermal expansion and contraction, it again may deviate, right? And it may again deviate in between. We have atmospheric conditions, right? Like fog, it would not able to work in a foggy condition, right? Light will not get passed through it, right? So we use the same technique of feedback in this FSO scenario as well, where we have a n number of lasers at the transmitter and a single aperture at the receiver side. Okay, fine. So we have a precoder thing here, we schemes here, right? So this feedback scenarios you can use anywhere, right? So here we have optimum values of weights with respect to the strong turbulence and moderate turbulence conditions, including the pointing error, right? Then in this FSO communication, we can't use orthogonal space-time block code. Instead of that, we use repetition coding, right? It have been tried and tested, but not working for this FSO communication. It remains work for terrestrial or RF communication only. So we use repetition coding in a FSO. Repetition coding means we're going to transmit same signal from all the transmit antennas from the aperture laser things. But as you see, it provides a huge gain, right? 17 dB gain is quite huge, right? To achieve the same bit error rate, we need to incur 17 dB in case of erroneous feedback, right? Here we have also evaluated the capacity as well, and we found the same pattern in the capacity, right? Okay. So we extended this work for the cluster, which we have already explained you for the RF communication. We divided the total number of laser into two cluster and selecting the best laser transmit from each cluster, right? It's quite generalized. It have been published in the transaction TVT. Yeah. So it have been explained here, and with the comparison of the number of bits it requires. TTLS means selecting two transmit laser selection. Okay. So as I've told you, divide the total laser transmitters into two clusters and selecting a best laser from these clusters.
Sorry for the interruption. This is the research paper article which we will be discussing in the very same session. So, sir will be discussing the codes and will be showing the MATLAB simulation for the same. So, are we willing to continue, or we can take a 10 minutes break and start it all over again? So we can have a break for 5-10 minutes so that even he gets refreshen up, and then we'll start with the simulation and the article discussion session. So we'll continue in next 10 minutes. It would be at 12, right? Thank you.
Okay. Slide show. Right. So let's resume this, and I will finish in. And then after this, we would see the MATLAB exercise. How do we implement the wireless communication scenario in the MATLAB, including MRC beamforming, uh, secrecy outage probability, right? All these things. So let's finish this first. Uh, Again, in this cluster-based transmit antenna selection scheme, we divide the total laser antennas into two clusters and selecting the best laser out of it. So this IP represents the maximum, the antenna, the laser antenna associated with the maximum intensity. In the FSO scenario, we called it as intensity instead of channel gain. And IQ represents the same for the another cluster. NC1 and NC2 is going to be LT by 2 for LT is even, and for odd it would be LT minus 1 divided by 2, LT plus 1 divided by 2 respectively. So in FSO scenario, instead of space-time block code, we use repetition code. Repetition code means we are going to transmit the same signal from all the transmit lasers. So for I1 greater than I2 greater than I3 greater than 4, the first scenario where we have I1 and I2 are the best two antennas out of the total lasers. However, since we divide it into two clusters, the I1 would be the best for the from the cluster 1 and I3 would be the best for the cluster 2. For repetition coding, irrespective of the intensity gain, which one the higher, we provide equal power to all the lasers. Okay. Whereas STLS represents single transmit laser selection. We are going to select the single laser having the largest intensity and giving all the power to that. So it means 1 0 0 0 means I1 is the highest one. So we give all the power to the antenna 1 with intensity I1. The proposed scheme says TTLS selecting two transmit laser. So one laser from each cluster, first cluster I1, second cluster I3. So 1 0 1 0. Let's see the second column where we have I2 is the highest one, right? Then I1, I4 and I3. It means from the first cluster we give all the power to the I2. So it means the last TTLS you can observe 0 1 and 0 1, the reverse of the first one. Fine. And based upon this, the how many number of bits it would require to select the two transmit laser selection is 2 log base 2 LT minus 2 for LT is even, and the other expression is for LT odd. Right. So here is the comparison between selecting the two transmit lasers and a single transmit lasers based upon the required number of feedback bits. For LT equals to 3, 1 and 2. For LT equals to 4, we have 2, 2, and for LT equals to 8, which we have already seen for the case of B2RS, selecting best two relay antenna selection, right? Single antenna selection would require slightly lesser number of feedback bits in comparison to selecting the two transmit laser selection. Okay. So let's recall one thing and then I will show you the graph. If we have the error in the feedback and we choose the wrong antenna or a wrong precoder, or we wrongly allocate power, right? So which one do you think would perform, TTLS or STLS, if we have a wrong selection? if we select a wrong precoder and allocate power to the wrong antenna, which would perform better, PTLS or STLS? TTLS, because we have to activate two antennas, right? Whereas in STLS we activate only single antennas, and if we select that only selected antenna which is in the bad fading scenario, so it would not give any communication result to us. However, in selecting two antennas in the erroneous scenario, still we have a scope of better transmission, right? So before moving towards the result section of this article, we modified that error tolerant scheme accordingly. We considered the four weights, since consider the four transmit laser selection. We have a four transmit lasers. We divided into the cluster of two lasers, right? Then we have a weights W1, W2, W3, and W4, right? So if we have a W equals to 1, it means we are giving equal power to both the antennas, right? It's a slightly modified version of the previous which we have learned for the RF communication scenario, right? Then it can be easily led to the generalized one with the help of this WK if IK is greater than LK is greater than L for K equals to L, right? Where K is 1 to 2 for C1 and WS for this T is for 3 to 4 to select the best antenna from the each cluster. So this is the input output relation what we are received at the photodiode, right, including the weights. So this is the case 1 where we have I1 is the highest one from the first cluster and I3 from the second cluster. So we use W3 and W4. This need to be understood. W1 when we have I1 is greater than I2, right? Right? And if we have a I3 greater than I4 for second cluster, we choose W3, right? Fine. This is, let's say, assume this is the correct case, right? This is the correct feedback case scenario. So what would be the other cases? Incorrect, wrong precoder selection cases. So we would have 3 wrong selection cases like this: W1, W4, W2, W3, W2, W4, other combinations, right? These are the incorrect decode of the feedback bits. So instead of, see, W1 is selected correctly from the first cluster, but W4 is selected incorrectly from the second cluster. In the another case, W2 is selected incorrectly from the first cluster, W3 corrected from correct from the another cluster, and last is the most severe one, wrong from the first cluster as well as wrong from the second cluster as well, right? And you can easily see the comparison between these graphs. You can find out this STLS is performing best out of other schemes for this 4x1 meso system, provided we have a perfect feedback scenario, right? Here we don't have considered eavesdropper, right? In the previous case, we have also considered eavesdropper, where I have told you single transmit antenna selection leaks more information towards the eve because confusion is less, right? Here we don't have considered any eavesdropper. That's why we can see the straightforward thing that single transmit laser selection outperforms two transmit laser selection in case of perfect feedback, right? As soon as we have erroneous feedback, you can see how the performance deviates for the single transmit laser selection, right? Fine. because of that diversity order. In case of error, we select only single transmitter, so diversity order would be 1. However, in case of error, if we are still selecting 2 transmitter, diversity order would be 2. So that is the difference between the slopes of these things you can easily observe. Fine. Now, for the MIMO case and for the larger number of transmit antenna selection case, including this modified error tolerant weighing scheme is depicted in this graph, right? It's a complex graph. So let's start with the RC 8 cross 1. As I've told you, RC means equal power allocation, giving equal power to all the transmitter selection, right? So this is represented by this blue asterisk. Then we have a TTLS 8 cross 1, right? So diversity order is same for RC 8 cross 1 and TTLS 8 cross 1. How much? For TTLS 8 cross 1 diversity order would be 8, and for RC 8 cross 1 again 8. You can easily observe the slope of these two lines, right? Slope is same, parallel to both, right? Both are parallel to each other. That's why we can easily say that diversity order is same. Then we have a 8 cross 2, TTLS 8 cross 2. What would be the diversity order for 8 cross 2? See, it depends upon the atmospheric turbulence conditions as well, but I am neglecting this to make you understand in a simpler manner. Let's say I am considering the RF communication here, then you can easily find out. For 8 cross 2, how many channels we have? 16, right? So we have a 16 options to transmit the same message, right? So you can easily observe the change in the slope, right? Change in the slope. The performance of this modified error tolerance scheme, which is represented this black, this right, 8 cross 1, that is lies between RC and TTLS, right? RC and TTLS. This modified error tolerant weighing scheme performance lies between RC and TTLS. So somewhat we are able to achieve the coding in while maintaining the diversity order. This is the whole crunch of this thing. We have 3 scenarios. One where we don't have any channel state information. Second, where we have full channel state information. Third, we have partial channel state information, right? So partial channel state information provides perform between these two, where we don't have channel state information and we have full channel state information. That is the first conclusion point. Second is, in case of erroneous feedback, selecting a single transmit antenna is not a good option, right? Third, to enhance the diversity order in case of error, we can select two antennas, two best antennas, provided the number of feedback bit would get increased. Fine. So these are the conclusions I have just explained to all of you. If you have any doubt till this point, you can ask. Then after this, I will start the MATLAB exercise to explain how to implement the wireless scenario. Any doubt till this point? Fine. Hmm. Yes. 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 That eavesdropper, the question is how come we can have a eavesdropper in the FSO scenario? So it's a special case where the eavesdropper lies close to the receiver aperture. So due to the beam divergence, it can extract the information. channel coefficient, H, yes. Hmm. Hmm. Yes, yes. Yes, the question is from this physical layer scenario where we have a eavesdropper and we may have the case where the forward channel, the legitimate channel and the eavesdropper channel values get similar to each other. Right. So it might be happen, but as I've told you, we are giving here the average secrecy outage probability, where we considered the scenarios where it may become equal, it may not become equal. So on a large average scenarios, it found that it not get equal. Yes, probability is very less. We have found with the help of the averaging, right? Or as we increase the number of antennas, we get more secrecy, more confusion towards the, as I've explained from the another thing where we selecting the best two antennas in the presence of the eve, right? Yes. Yes. That secrecy outage probabilities comes from the information theory only. Yes. We have used the same Shannon capacity theory. I will show it in the MATLAB code. So all of you aware about the MATLAB? Okay, so I am going to start with a very simple exercise. Forget about the wireless for some time. We just need to simulate the bit error rate versus SNR of AWGN over BPSK modulation. Right. Okay. So here we have a single transmitter and single receiver. Both are connecting through a wire. Okay. Where we have a AWGN, no fading, no wireless. Fine. And we are going to transmit our signal with the help of the BPSK modulation. Right. So first of all, we need to set the how many bits we are going to transmit, or you can call it as the iteration as well. So n is equals to 10 raised to the power 6. I have just arbitrarily taken it as 10 raised to the power 6. Right. Then to modulate our bits in the form of BPSK, we started with a rand 1 comma n greater than 0.5, which generates random bits between 0 and 1, right? Which generates bits between 0 and 1. So why do we are using rand here? Random, fine. Rand also provides the 0 and 1 in the uniform distribution manner, right? We are going to generate 0 and 1 in the form of uniform distribution manner. That's why we use the command here rand, right. Then this value of a would be 0 and 1, right? If we are not using BPSK, we are using BASK, then we achieved our modulation, right? But we need to convert this 0 and 1 into -1 and 1. That's why we further write s equals to 2a minus 1. When a is 0, we get s minus 1, and when a is 1, we get s equals to 1. So we achieved +1 and -1 accordingly, right? So we have our 0 and 1 here with mapping with -1 and 1. Right. Then we need to choose the range of the SNR in dB. I choose a 0 to 10. You can choose it anything with the step size as well. If we have written here 0, this colon 10, it means the step size would be 1, right? 0, 1, 2, 3, 4 as a go to 10. Fine. Then as I told you, we are considering y equal to s plus n, AWGN. For the AWGN, y equal to s plus n. right? So we have our S with us. Now we need to generate N, AWGN. So that AWGN 1 by square root 2 rand n 1 comma n plus 1 iota rand 1 comma n. Let's forget about this 1 by square root 2. Focus on rand n 1 comma n, right? Just focus on rand n 1 comma n. मैटलब खोलो, मैटलब खोला होगा, हाँ ठीक है। लिखो यहाँ पे n की वैल्यू लिखो पहले, कमांड विंडो पे लिख दो, हाँ कमांड विंडो नीचे है भाई, हाँ n इक्वल्स टू 10⁻⁶, ठीक है। इसका फॉन्ट साइज बड़ा करना पड़ेगा, आता है फॉन्ट साइज बड़ा करना? डिफॉल्ट तो इतना रहेगा। ये वाला तो बड़ा हो रहा है ना, चलो इसी को पढ़ लेते हैं, ठीक है। सो n इक्वल्स टू 10⁻⁶, ठीक है, ऐसे लिखते जाओगे, करते जाओगे, सेमीकोलन एंटर, फाइन। देन राइट x इक्वल्स टू rand n, x इक्वल्स टू rand n स्मॉल n ब्रैकेट 1 comma n, 1 comma n सेमीकोलन, एंटर। m इक्वल्स टू m स्मॉल m इक्वल्स टू मीन ऑफ x, MEAN, mean bracket x. What do you think? What would be the mean of this? See, we have seen rand. Now we have a rand n. So there should be some difference between these two commands. Na? Previously, I have told you rand represents a uniform distribution. Rand n is normal distribution, right? Normal distribution का mean क्या होता है? Gaussian curve, right? We have a Gaussian curve, mean at 0, right? Mean at 0, right? तो इसको होल सेलेक्ट करो, राइट क्लिक करो, इवेल्युएट करो, सिलेक्टेड को पहला ऑप्शन नहीं, राइट क्लिक करके जो पहला ऑप्शन आ रहा था क्लिक करो, नीचे क्या आया कमांड विंडो पे, एंटर करो, बताओ जतिन बोलो, इसको कॉपी पेस्ट कर दो ऊपर, बड़ा हो जाएगा, तो देखो ऊपर का बड़ा कर रखा है, जूम कर रखा है, हाँ ठीक है। तो मीन की वैल्यू, m की वैल्यू कितनी होगी? 6.8812 e raised to the power minus 0.5, close to 0, fine, close to 0, right? Now find out the variance. v equals to var, v equals to, ऊपर वाला भी डिलीट करना पड़ेगा, v equals to var x ब्रैकेट x, हाँ इसको करो सेम, रन करो, सिलेक्ट करो, इवेल्युएट करो, कॉपी पेस्ट कर दो, हाँ मीन कितना है? नहीं -8 का 0.99 है ना, 8 नहीं है, 0.9991, क्लोज टू 1। नॉर्मल डिस्ट्रीब्यूशन का हमें ये पता है, मीन इज 0, वेरिएंस इज 1, वी आर गेटिंग दिस, राइट? कोड पे आ जाओ, मतलब मेरी पीपीटी पे आ जाओ, हाँ। So here we are writing here n equals to 1 by square root 2 rand n 1 comma n plus 1 iota into rand n 1 comma n. तो इसका n का मीन और वेरिएंस कितना होगा? What would be the mean and variance of this? First rand n 1 comma n, mean is 0, ठीक है। Second plus 1 iota rand 1 comma n, rand n 1 comma n, उसका भी मीन 0, 0 plus 0 0, तो इसका मीन तो 0 हो गया, फाइन। व्हाट वुड बी द वेरिएंस? वेरिएंस ऑफ फर्स्ट इज rand n 1 comma n is 1, second one 1, तो 1 plus 1 2। व्हाट अबाउट दिस 1 by square root 2? स्क्वायर हो जाएगा ना इसका, तो क्या हो जाएगा 2 by 2। अब इसको कॉपी कर लो, इस लाइन को, n वाली लाइन को कॉपी पेस्ट कर लो, n वाली लाइन को नीचे n, हाँ इसको कॉपी पेस्ट करो, कमांड विंडो पे जाओ, या फिर ऊपर ही लिख दो, दिख नहीं रहा ना नीचे, फॉन्ट साइज इसका बड़ा, ठीक। एन को डिफाइन करो, एन कब नहीं, अपर केस एन को डिफाइन करो बस, सही है, सही, डिलीट कर दो सब कुछ, अपर केस एन को डिफाइन करो बस, नीचे ऊपर, हाँ ऊपर, हाँ अपर केस एन 10⁻⁶ कर दो, ठीक है, ठीक है। अब इसको एग्जीक्यूट कर दो, ओके, ठीक है। अब इसका मीन और वेरिएंस का कमांड लिख दो, एन का चलने दो, m इक्वल्स टू मीन ऑफ n, v इक्वल्स टू वेरिएंस ऑफ n। सेमीकोलन लगा दो n के, n वाली लाइन के आगे, सेकंड लाइन के आगे, सेकंड वाली लाइन के आगे सेमीकोलन। वैल्यूज नहीं दिखाएगा ना सेमीकोलन लगाएंगे तो, इस पे नहीं, इस पे नहीं लगानी, सिर्फ इस पे लगानी है बस, नीचे वाले से हटा दो बस, कर दो सिलेक्ट, सिलेक्ट करो सबको, okay fine, so we have a mean near to 0 and variance equals to 1, fine, यहाँ तक आ गया। तो this is the purpose of multiplying with 1 by square root 2 to normalize the variance, ठीक है, ppt पे आ जाओ, fine, okay fine, now we are start to at the receiver side what we are going to receive, ठीक है। This again, to normalize this SNR, mean and variance, we apply a 10⁻⁷ SNR dB divided by 20, because here we are going to convert our dB into linear first, ठीक है, and then we have you have already seen y equals to under root of EB S plus N thing, right? To normalize this SNR, we just applied this, okay. Now the most interesting part is detection at the receiver side, right? So at the detection side, there are multiple logic you can use. This is one of the logic. Okay. Absolute of y minus this. So this b is going to equivalent with of n, isn't it? This variable b is equivalent to n. We have just shifted and isolated n here with a sign. B and c, you can observe the sign of b and c, which is -1 and +1. Right, that makes the difference of with the help of s, because s is bpsk, +1 and -1, right? So if we have detected b, it means s का value क्या है, +1. If s is +1, then we would have y minus 10⁻⁴ SNR dB%, right? And if we have plus, then s is -1. So b and c are mapping with the n noise. So at the detection, what we are looking for? Minimize the noise. Where we get the minimum noise, that would be the detection value. So you can use here the logic of minimum as well. However, I have used loop, if else loop here. If b is greater than equals to c, we would decode it as -1, right? Whereas +1. Fine. Next slide. Right, fine. Alternative method, then at the side, अब हमने क्या कर लिया, we have decoded. Now we are looking to how many errors we have while decoding. ठीक है, we are just counting how many errors. So focus on this NERAWGN line. Size find s minus yy. Let's talk about this command find s minus yy. What it does, it finds the number of non-zeros. It finds the number of non-zeros. ठीक है, ये है, ये ठंडा ही है. Find s minus yy means what we have transmitted, s. What we have decoded, yy, right? So how many non-zeros we have? For example, if we have 10 non-zeros, ठीक है, so this command find will provide it in the form of vector. 1 cross 10. So which dimension we need to choose? Second dimension, right? So that's why we have put here another command, size find s minus yy comma 2. It means we need to take the second dimension. 1 cross 10 hai agar, then we need to choose the second dimension, means number of columns. So 10, right? So this is the average bit error rate of AWGN which we have simulated. Then we all know the expression of average AWGN bit error rate in the form of Q function, Q under root of twice of SNR, right? So if we execute both of these, plot with the help of the semi-log, we get the next slide. This, you can see that simulation and analytical are matching each other. It means we have simulated in a correct manner. ठीक है? Now इसको स्लाइड शो, अच्छा उसमें हमने दिखाना है ना, ठीक है, तो हो गया, स्लाइड शो करो, स्लाइड शो करो, हाँ अब ठीक है. Now in the second exercise, here I put a 2 cross 1 VISO system where we use the wireless scenario, right? H1 and H2, right? H1 and H2 is also a complex Gaussian number where we have choose here the normal Gaussian with mean 1 and mean 0 and variance 1. Then we have a beamforming weights used to make this independent, W1 and W2. So effective transmitted signal would be W1 H1 S1, which is accommodated in the variable X1, and W2 S2 S1 in variable X2. Remember, we are transmitting same signal from both the antennas. That's why we have here S1 and S1. Again, we are using BPSK, so the process of mapping is same, right? Then we have a AWGN, then we have a received signal. What we are going to, we received signal in a combination X1 plus X2, the last line, y equals to 10 raised to the power SNR divided by 20, then X1 plus X2 plus N, right? Next slide में गलत है यहाँ से, ठीक. Then we have effective channel matrix, which are going to be square root of norm of H square, norm of H square, right? Again, detection, absolute of y minus h whole square, y plus h square. Compare this B and C to decode +1 and -1, right? Same again, size, find yy minus S1 to, fine. Then we have a analytical expression. You can find out this analytical expression in many number of papers, right? So these two are matching each other, quite evident that our simulation is correct. Okay. Now similarly, we have a 1 cross 2 system which we have already learned in the first session of PPT, right? In a similar manner, we have a H1, H2. Instead of N1 here, we have a N1 and N2 because we have a 2 receive antennas. So we have a 2 noise, N1 and N2 separately at both the antennas, right? So outage probability. So what do you mean by outage probability? Let me define first what do you mean by outage probability, then we will go with the code. We used to say when we have an electricity issue, right? When we have an electricity issue, we say outage ho gaya, right? Right. What do you mean by that? Outage ho gaya. It means connection or electricity is not appropriate, right? So in outage probability thing, in a communication scenario means that the received SNR is quite less than the threshold value of SNR, which signifies that the decoding process is not going to be appropriate since the value of SNR is less than threshold. So whenever I have this probability that average SNR is become less than the threshold SNR, we call that outage probability. So here we are going to count how many number of times it happens that the average SNR becomes less than the threshold SNR. Then we average it out of total and then plot it. Okay. Okay. So here we considered a 2x1 scenario. Start with threshold SNR. I have selected it as 1. You can select it as 2 as well. Fine. Then again defining the SNR in dB. Then the empty arrays to store the values. Then H1 and H2. Then absolute value of H1 and H2 for the beam forming scenario we have considered. Fine. Then we started with the first value of SNR. Look at this loop, for loop, jj equals to 1, length of SNR. For jj equals to 1 means select the first value of SNR, which we have started with 2. At 2 dB, we transmit 10 raised to the power 6 symbols, right? And find out how many times it happens that we have a SNR less than the threshold. So we are going to count that thing, right? We are counting how many number of times the received SNR is less than the threshold value of the SNR, right? Then average it. This P1 NR reflects the analytical outage probability as mentioned in the comment, and it also get matched with each other, right? Now secrecy outage probability. The question arises how it is related to the information theoretic point, right? How the information theory coding helps us to secure the system, or it is the same thing or not. Yes, it is the same thing, same scenario we have used as the Shannon capacity, C equals to log base 2 1 plus SNR, right? Right, okay. So here we have generated the channel coefficients for the Alice to Bob legitimate channel, and HE1 and HE2 represents the channel for the eavesdropper, right? And for the outer scenario, we need to count how many number of times we have the scenarios where the received SNR values falls behind the threshold SNR. We have fixed the SNR value of the eavesdropper link here. Fine. You can see here the CS, that is the instantaneous secrecy capacity. You easily remind it with the help of the Shannon capacity theorem, right? Log base 2 1 plus S. S represents the SNR, instantaneous SNR of your Alice to Bob, and SE represents the average instantaneous SNR from Alice to Eve. Okay? Both have two independent channels, right? Then we need to find out how many number of times it have been happened that CS is become less than RS for the secrecy outage probability, right? RS represents the secrecy rate, targeted secrecy rate, right? Then we have an analytical expression. This analytical expression is related to the system model I have showed you with the emojis, right? So these two are also matching with each other. Then first I need to show you this graph, and then I will explain you the code, right? So on the last minute, I decided to include this in the MATLAB exercise because it's quite important how to find the optimum value of the A, right? I have choose here outage probability performance. What do you think? Outage probability should be large or less? Outage probability high होना चाहिए, low होना चाहिए? Outage probability high होना चाहिए, low होना चाहिए? Probability of a system get into the outage scenario should be low, right? Should be low. That's why we are getting a convex where otherwise it would become concave. We need to find the maximum at which it's getting maximum, right? Since it should be low, that's why we are finding the minimum value where it becomes the lowest, right? So it's quite difficult to find out this optimal convex curve smooth with the help of the simulation, because in the simulation it becomes iterative, so it gets fluctuated, right? So instead of that, we use a numerical minimizing method with the help of the analytical expression which we have derived in the paper, right? So we use that expression of the secrecy outage probability, which is a function of A1 and A2, and we vary this A1 and A2 as we have seen from 0.001 to 1, and find out uh, the minimum value of SOP for each scenario of PC. I think here, yes. See the first line, PC 0.8, 0.9, 0.95, 0.99 and 1, right? These are the correct feedback probabilities. So for each value, we need to find the optimum value of A1. So we fix the value of PC, then vary the value of A1 and A2 with small step size 0.01, right? And find out where we get the minimum value of SOP, and we get the graph, convex graph like this. Now, feedback. How do we implement this feedback thing on the MATLAB, right? So, with the help of feedback, what we are doing? What we are doing with the help of the feedback? We are estimating the channel state information, right? We are estimating the channel state information at the transmitter. Then what next? We are selecting the precoder matrix, right? So I will coarsely go through it. First, we need to fix the PC value. Then, accordingly, the optimum value of the, here we have considered the three cases only. PC1, A1. It means best transmit antenna selection, right? PC 0.95, and still we are allocating whole power to the single antenna. It means best transmit antenna selection with erroneous feedback. PC equals to 1 and A equals to 0.5. What does it mean? If we select A equals to 0.5 for 2x1 system, what does it mean? We are giving equal power to both the transmit antennas, 0.5 and 0.5, right? Right? Okay. So here we have you can see in the middle part where x is equals to rand, right? And if x is less than PC1, so we would select the instantaneous SNR accordingly. And this is the whole logic of the feedback bit. You can't see the feedback bit here, but you can easily analyze with the help of this rand. If x is rand, it provides the random value between 0 and 1, right? As I've already seen, I already show you previously. Okay. So x is less than PC1. If x is less than PC1, matlab PC1 is greater than that random value. So we are having luxury of using the correct feedback bit, right? So we have instantaneous SNR with correctly received feedback, right? So this is the logic of implementing feedback on the MATLAB. Then we have an analytical expression, right? And these are the graphs. UP represents the uniform power allocation, BTS with perfect feedback, and BTS with error. BTS with error means selecting the wrong antenna and giving whole power to that wrong antenna. So its performance deteriorates, right? So this is all from the MATLAB exercise. If you have any question, you can ask now. Any questions?
Thank you, sir, for such informative session. Now, I would like to request Dr. Rubina Vora to kindly come and felicitate our chief guest. So it is requested to all, please kindly come forward for a group photograph.